Vanakkam and welcome to the day 4 of 5-day FDP on additive manufacturing from 3D printing to factory floor. The track for the day is innovation in additive manufacturing, and the first session will be completely focused on innovation in different aspects of additive manufacturing. The title is entitled with innovation in medical devices, space and defense application, and that will be completely presented by Altem Technologies. The presenter for the day will be Mr. Shubham Gupta, Senior Applicant Engineer, 3D Printing, followed by Ms. Aishwarya Shirur, Technical Specialist, 3D Bioprinting. And I will also like to express my gratitude to Mr. Sridharan from Alton Technologies for arranging us this wonderful session. Over to you, sir, Mr. Shubham Gupta. We'll start.
Yeah, thank you so much. I'll just share my screen.
Yes, sir.
So I hope screen is visible.
Yes, sir.
Okay, thank you very much for a brief introduction. Hi everyone, I welcome you all in this session. A very good morning to all of you. As Sarah has introduced me, my name is Shubham Gupta and I represent Altum as a senior engineer for application and support in 3D printing. So basically today's our session is to discussion on the innovation in aerospace, defense and healthcare applications specific to 3D printing. Basically I'll show you as I go through into the presentation. I'll show you different Indian case studies of the companies in which they have implemented 3D printing solution for their design and innovation work. So let me quickly brief about Altum. We are basically established in 2011, Bangalore based company. Altum is a 3D innovation platform company. What that mean is basically we have a set of tools in terms of software and hardware in our portfolio with which we can solve most of the design related challenges for any of the organization. You can see a few of the products listed over here from software side as well as the hardware side. Like we have a CAD solution to prototyping solution as well as reverse engineering solution and analysis solution. So I'll not go deep in or in the details of these products. You can just look over it. So let me quickly switch to our basic key focus of today's session. I'll start with the aerospace and defense area and will show how companies are using 3D printing solution for the aerospace industry, right? Basically we know that in aerospace industry each and every material or a component which is going to be used for manufacturing an airplane, or which is or it's going to use any of the component which is used for the aeroplane industry, aerospace industry is a standardized one. Like there are some sort of certifications on the specification side of a material, or I can say there are some material properties which each and every component has to be fulfilled before using it into a aerospace application, right? So a general question came in our mind then how FDM based plastic 3D printing solution could be a good fit for aerospace industry. How those plastic components can be used in the aerospace industry. So basically I have described a picture over here. You can see the different areas where a 3D printing solution could be a great fit, be it a prototyping, or I can say as a manufacturing aid for a jigs and fixture, or at some application as a low volume manufacturing part and use part as well. So basically you can see the printed picture, the printed photos as well, the 3D printed parts photos. You can see this is a cabin vent which basically is helpful to maintain an environmental control system in internal cabin, right? So windows trim, a cup or a tray holder, or I can say a bezel screen, display screens, camera adapters, electrical housing. So there are so many components in the cabin of an airplane, where a 3D printing could be a good fit, right? Where a 3D printing could be a good fit for a prototyping or for a low volume manufacturing. So how since these all are plastic made, right? So how they are going to be used directly in an aerospace. So basically there is a solution called a material which is an Ultim 9085, an Ultim 1010 material. It's basically FA approved materials which can be directly used for transportation or an aerospace industry, right? And we can 3D print a part with that material. We can fit into an aeroplane and we can fly. So that much possibilities are now available within the 3D printing industry, right? So in coming slides, I will show you how companies have used these materials, and the what is the hardware side with which we can 3D print these material, and we can basically directly fit it into a plane and we can fly. So first, what are the challenges that aerospace industry is currently facing while manufacturing a component, right? So the first challenge is the long lead time. Basically, they are dependent on some sort of suppliers to get their specs, right? And all the components which are basically being used in an airplane is machined by a traditional way, or CNC cutting or tooling. Those kind of traditional processes are being used for the development of the product, right? So this all leads to a long lead time. So we companies have to basically wait for a months, like couple of months to get their part, and all this manufacturing is done by a labor. Like there is a lot of labor intensive work involved for the manufacturing of these kind of products, and as well as the operational expenses are too high, right? So apart from that, basically we know in a one airplane there are thousands of components installed within a one plane, right? So for each and every component, companies have to make the space for that inventory. Like they have to keep all the spares in stock for the future requirements. So space is also a big concern for the companies. Like they have to maintain a proper inventory. They have to keep a track on each and every spare when it is going to be out of stock, and they have to again reorder from their vendors, right? So there are so many challenges which are involved within an aerospace industry. And then what is the solution for all these challenges? The solution is the application of additive manufacturing in the aerospace. Additive manufacturing gives us a cost effective and well as efficient solution for these kind of challenges. How basically there is a study, if the company is able to reduce a 1 pound of weight from an aeroplane, then they can save a 14,000 gallons of fuel each year, right? So 3D printed part is so lightweight, since they're plastic, there are complete plastics, and there are software settings with which we can make the part hollow. We can give a honeycomb structure, or we can optimize it for the best strength as well as less material, right? So basically a very lightweight part we can produce, we can save material, and the end product is very cost effective, right? And efficient as well. Efficiency means basically we can make or we can 3D print our product on demand. Like we are not making all those 3D printed parts in stock. Whenever the requirement came, we'll just give a command to our machine, we'll import our design file, we'll just give a command, our part will get ready in a 1 or 2 day, right? So basically we can there is no need to we there is no need to keep all the spares in inventory. We can print our part on demand, so the solution is efficient. So with these all these challenges, we can reduce basically a lead time from 6 months to, let's say, 6 weeks. Because instead of depending upon tooling or any vendor or outsourcing, we have our 3D printer in house. We can give a command and part will get ready in a 1 or 2 day, right? So third solution is basically materials. There are a lot of materials available within the FTM 3D printing, which with which you can do your prototyping. You can print your jigs and fixture for a manufacturing aid. And there are some sort of materials which are approved by aerospace and transportation industries to be used directly in an airplane, so that you can use those materials as your end use part, right? So basically all these challenges can be tackled with the help of FTM based additive manufacturing solution. So Now there is an example. This is an Indian case study from gas turbine research establishment, basically in Bangalore. So the idea was they have basically developed a full-scale mechanism prototype for their Kaveri engine, which was basically used in an actual Tejas aircraft. Right. So this is the 3D printed full-scale model in plastic. You can see the image over here. Right, the greatest challenge which they were facing was the, like, they want to optimize this engine for the locations of sub assemblies, because there are so many components are involved within this particular one engine. Sub assemblies are there, so they want to optimize the location of each and every component of that part so that they can minimize the piping length. Right, so you can see over here, I have mentioned, like, there are 2500 components are there within this assembly. And if they are going it to the outsource or some vendor, or if they are using a traditional way of machining this part, the lead time was almost 1 year. Right, and if they are not going into a prototyping, they are just seeing their part on a screen or a CAD software. uh, there is some certainty that they may missed some few areas where, like, in future they get challenged while manufacturing this kind of component. Right, so what was the solution that they have used? They used an Stratasys Photos 3D printing solution, which is an FDM based 3D printing application. So basically they have printed a full assembly in FDM based 3D printing with ABS material. It's a engineering thermoplastic material, right? And because with Photos printing solution, basically we have a special material called water soluble support, right? So basically we'll print our part wherever intricate geometries or hollow sections, or I can say overhang geometry is there. We can The support material will print at that particular area. Then we have to dip it into a water tank, and that support material will automatically get dissolved. That is a concept of water soluble support. So with that option we can print any complex geometry without any tooling. Right, so you can see over here, because with the help of that soluble support, they have enabled of to printing this full complex geometry of piping. Right, and if they compare the lead time from a traditional way to an 3D printing, so initial lead time was 12 months, which is 1 year, and then with the help of 3D printing they have developed this part within a 6 weeks. And you can even see the cost comparison between the traditional way of machining as well as the 3D printing. Right, so this is the full image. This is a clear image of their Kaveri rapid prototyping model. You can see over here the intricacy of this part. There are so many piping section over here. There is so many complex geometry, and they are able to print it in a full scale model with their photo solution. And then they have dipped this part in a tank where that support material automatically get dissolved. This is how possibility is there with the help of 3D printing solution. Right, so this is the second example again from CAIR Center for Artificial Intelligence and Robotics. Basically, again in Bangalore, they are into developing of smart robotics, and they have developed so many models of different robotics that they are basically using for their surveillance activities. The first example is this miniature unmanned ground vehicle. Right, so basically it uses a tracked locomotion to negotiate between the rough terrain as well as the urban terrain, between the steps and the staircases. Right, the idea is basically they have used again a photos 3D printing solution, and they have printed this complete model, the main body as well as the electronics housing in which batteries, sensors, and other cables are basically mounting. So they have printed this whole assembly again with FDM 3D printing solution. Right, the second example is again from CAIR. This is a snake robot, basically having a 14 different segments, or I can say active joints, which gives this body as a whole uh, locomotion. Which what that mean is basically this part can move horizontal as well as in vertical direction, and they have fitted a video camera over there to get the actual video feedback while doing surveillance. Again, the head and the tail segment of this robot is 3D printed on Fortress FDM 3D printing solution, and basically this is a very complex geometry, and this is again possible due to the availability of water soluble support, right? The third example is this wall climbing robot. Basically, they have used an impeller design to get a suction so that it can basically climb that wall. And the impeller body was again 3D printed with the FTM technology on an ABS material. So these are the three examples from CIR. Apart from that, they have printed this again 6 and 4 robot again for some surveillance application, and again they can do a omnidirectional motion capability, and again a full body of these robots, the main body, the legs, everything is 3D printed with alter material on their Fortis 3D printing solution, right? So these are like the two examples which I have shown. The first one is from GTRE, second one is from CAIR. This is the third example. This is from HAL, Hindustan Aerospace Limited. So basically, they have used 3D printing solution for the composite tooling. They have Fortis machine in house, and what is composite tooling basically means they have printed their model on let's say one material, and then they wrapped that particular model with the carbon fiber sheet. That's for an example of a carbon fiber composite tooling, right? So they have printed this model in a material, and they have wrapped that carbon fiber sheet on it, and after that this is a special material. We have a material called ST130 which is used for sacrificial tooling, right? So basically they dipped it into a pot, and then that material get dissolved, and the left out part is the wrapped carbon fiber part, right? So this is called composite tooling. We cannot print a direct carbon fiber, let's say, right? So we'll print our dummy model, we'll wrap that sheet over it, and then we'll dip it into a tank. This model will get dissolved, and the leftover part is this fully wrapped carbon sheet. So then they have used this for wind tunnel testing. Like they have put sensors and all the equipments, and they have run the wind tunnel uh, settings over there to check this functionality of their part, right? This one is an example from ISRO satellite center. Basically they have printed a scale model of their satellites to check the to get the concept verification of their idea of the satellites, right? They have again used composite tooling application for few of their design models. Right? These are two again case studies from the aerospace side. This is one case study from UTC Aerospace in Bangalore. They have two Fortis machines, strategic 3D printing solution. So basically, the idea is they want to make a nozzle, which is basically kind of a flame collection system, right? Fume collection system, I can say. So the need, what was the need? The need was to basically reduce both cost and time to market as compared to a traditional way of machining. First need. Second thing was they want to optimize the productivity by in-house. They don't want to depend upon some other vendors or the machining side, and they want some material which is good heat resistive property, right? Solution was again a Fortis 450 using Ultim 1010 material. So this material is heat resistant as well as chemical resistant and strong enough to withstand the harsh factory environment. So you can see this was the machined part of that particular fume collection nozzle, and this was printed in ABS material just for prototyping, and then they have printed this final model in Ultim 1010 material on their Fortis machine, and this works as an end use part, right? This material is and capability of a heat this heat deflection temperature of 220 degree, right? So basically that much heat resistant material they are looking for, and they have printed this part in alternative material. The time saving for this was is as compared to the traditional one was 95%, and the cost saving was almost 63%. So these kind of application, be it a prototyping or be it a tooling or be it and use low volume production, 3D printing is helpful in the aerospace industry. I have one more example over here. This is basically China Eastern Air line example. They in 2015 they have basically launched a new Boeing 777 passenger plane, and there was an error in the printing of an aircraft seat. You can see there was a misprinting over there on that symbol of the seat sign, right? So basically, if they go into again a traditional way of manufacturing, or if they go to the original factory to get these pairs of this seat sign, the waiting period was almost 180 days, and it was too expensive. So basically they again used a solution from Fortis 450, from a 3D printing solution they have used, and printed this model in Ultim 9085 material in just 3 days, and they have basically used for that rectify that particular error. And after 1 year, they within a 1 year, I can say they have produced more than 300 finished parts for assemblies in an aircraft cabin, right, including the mounting brackets. This is a mounting bracket for holding an electronic device, right? Apart from that, the back supporting mounting device, seat armrest, door handles, covers, and some other interior parts they have printed in a low manufacturing, as a low manufacturing, and they have directly fitted into a aircraft, and like that they have used 3D printing in their design activities, right? So this is one more example from same China Eastern Airline. This time they have basically developed a business class bookshelf. Basically, you can see over here it was damaged. You can see over there is a crack on this bookshelf due to the food trucks collisions and all. So instead of again going to the outer vendor of the original factory, they have 3D printed this complete model, and they have installed it within a aircraft, right? And they have used again 9085 ultra material to get this part. You can see over here this is a door handle which they have printed, and some other brackets or mountings which was 3D printed on the Photos machine, right? So this was the till now we have covered the aerospace and defense application, where a 3D printing could be a good fit for prototyping, aerospace prototyping, as well as the tooling and the end use part, low volume end use part. So from now on we'll basically switch into the aerospace, this medical section. From aerospace now we'll switch into a medical section where we'll see how 3D printing could be a good fit in the medical line, right? So let me just quickly go through the different applications where 3D printing could be a good fit in healthcare industry. And the first one is the anatomical model. What that means is the surgeons or the doctors can 3D print a complete human anatomy for the surgical planning, or for the surgical training, or for the as an education models. They can print a heart tissue, they can print a bone, they can print a brain model, they can print this hand you can see over here with all nerves and bones, to get the idea of how they are going to treat that particular surgery, or how they are going to plan that particular surgery, right? Second application is the medical device testing. They can print anatomy, as well as they can test it with the help of their medical devices. Basically, the materials which are available within the medical line, they gives a complete biomechanical properties which our human anatomy gives, right? So basically they can test a complete anatomy with their medical devices. This is one design and engineering application. Third is the medical tooling, with which they can 3D print a patient specific guides, a surgical guide, I can say, right? We have seen in a dental application, drilling is the common, right? So they can print a drill guide for that particular application. So fourth one is the medical devices. Again, they can print their prototype of their new development of medical devices. The first one was the testing of that anatomy with the medical devices, and this one is the prototyping of their medical devices, which they are basically new development, I can say, right? So these are the four different areas where 3D printing is helpful in the healthcare application. So, what is the workflow of 3D printing in medical line? The first starting is the medical scan, which is basically an MRI or a CT scan, right? So doctor or surgeon can do a MRI or a CT scan of that particular patient, which gives us a DICOM data. DICOM is basically a digital imaging, right? We have seen our X-ray in a 2D sheet, right? DICOM is a bundle of those sheets. I can say 100, 200,000 those sheets, right, in 2D. Then basically those DICOM data will get import into a medical software. Here I have shown you a materialized mimics. There are so many softwares available commercially as well as open source, right? So that DICOM data basically get import into a 3D medical software, right? And that medical software convert that data into a 3D model, which is basically a segmented STL files, right? Because for 3D printing we need a STL file or any CAD file, right? We cannot print 2D drawing or a 2D image, right? So basically MRI scan we import it into a medical software, and that medical software gives us a segmented STL file. That STL file will import it on our printing software, and our machine can print that particular anatomy, be it FDM machine or any other machine. That STL file will get printed, right? So instead of basically seeing, you can see this image, instead of seeing that it in 2D, that lung model, now surgeons or doctors can get the physical 3D model with the help of 3D printing, right? So let's say this is for internal geometry, right? Internally we need any anatomy, so we'll do MRI or CT scan. Let's say we need a face of that particular patient. There is some disease on that face, and we want to need that 3D model of that particular face. Then there is a technology called 3D scanning, with which we can scan that particular face of that patient, and that data will that 3D scanner will gives us a data of an STL file, right, within an STL file, and then we'll import that STL file in our printing software, and our 3D machine can print that one, right? Now there is one more way. Let's say there is some accident case in which a patient has lost the basically anatomy, right? So we'll again scan, like we'll again do an MRI or a CT scan, right? Then with the help of this 3D medical software, we design that particular anatomy, right? You can see over here the patient has uh, this one lost this side of their face, and then we have reconstructed with the help of this 3D medical software, and accordingly we'll plan that surgery. We'll 3D print that anatomy, and we'll plan that surgery. So this is how medical this workflow works, starting from a CT or an MRI scan to a segmented model STL file to a 3D print, or from a facial scan we'll get a 3D model and we'll 3D print it, or again from a CT scan we will design the anatomy and we'll reconstruct the anatomy and we will 3D print it. So this is a concept of medical 3D printing, right? So I will show a video over here with which you can basically understand the idea of what we do once we get a 3D model. Basically, this is a 3D model in a multi-material. Like this portion is a rubber soft material, and this is a complete hard material. So you can see on this dummy 3D printed model, surgeon is practicing the surgery, right? You can see instead of using a human anatomy or an animal anatomy, the surgeon is basically doing their OT practicing on that dummy 3D printed model. So as I earlier told, the materials which are available within the medical 3D printing are so real that they gives an actual biomechanical properties of a human anatomy. So a surgeon can basically observe, and like they can do everything which they want to do on a human anatomy. So you can see now they have put the telescope in that printed model, and they are viewing everything, that arteries and left ventricle, or all those things in that particular uh, anatomy. So they have inserted their medical device, they are doing the actual surgery which they are going to do in that operation theater. So this is basically a kind of surgical training for the new joinees or for trainers, right? This is one example. Second is basically there is one more video in the dental side. So this is from a dental engineering laboratories where they have 3D print a complete dental a complete tooth set, you can see over here. Then they are processing the implanting or the root canal treatment. So you can see the gums are printed with a soft material, right, with actual color and texture, and the teeth was printed again in a hard material with texture. So they are doing a complete surgical training on that 3D printed model. For a new, I can say, to train the surgeons, they are using 3D printed models. So basically, this gives a proper visualization of the pathology or the anomaly of that particular anatomy. Multicolor 3D printing gives you an idea to detect the defect better. Right. Even with the combination of soft material, you can simulate the actual surgery. With the combination of soft as well as hard material, you can simulate the actual anatomy, and you can accordingly train yourself or someone, right? And these kind of models are helpful to even print because these are biocompatible materials. There are few materials available which are biocompatible, so you can basically directly print an implant guide or something in a 3D printing, and you can fit it into a patient mouth while treating the surgeon. So you can see over here the materials are so real, they are giving a real feedback while doing a surgery. Right. So how this happens, basically how a 3D printer can print a hard material as well as soft material. Basically this technology is completely different from the FTM one. This technology is a polyjet technology, which is a basically polymer jetting. Right. So in polyjet machines, we can mix up to 7 different materials at once in a single geometry, and we can create more than 5 lakh colors in that particular design. Right. So you can see over here, this is a print head, and with 8 different heads attached in that particular assembly, with which we can directly jet 7 different materials. Let's say one like 2 to 3 hard materials, one soft material, one clear material which gives you a transparency, and support material. Like that, machine will automatically mix all those materials depending upon the settings which we have given in the software side, and machine will jet those materials layer by layer. Right. So with the help of Pagija technology, we can print a skin soft tissue or nerves soft tissue in different colors. We can print a skull as an hard tissue, teeth as an hard tissue, or even we can print a combination of soft as well as hard tissue in as in a spine model. So this is a one complete model in printed in a one go on a machine. So soft as well as hard as well as combination of all those materials, including different colors, can be now possible with the help of 3D printing, and this can be used for an as an education model to train someone regarding the anatomies. This can be used for surgical planning, right? Now again this one more example from here. This hard tissue, the skull was printed in a rigid material. Again, the tumor was printed in a clear material with semi rigid property, and nerves are printed in a soft material to basically to show the difference between the different anatomies. Right. So what are the examples, or I can say a patient point of care healthcare in healthcare application? This is one example from AIMS Delhi. AIMS Delhi have 5 different 3D printers in their 3 departments. They have printer in dental, neurology, as well as orthopedic department. So and they have used 3D printing technology for this surgical planning of partial nephrectomy. Basically, in partial nephrectomy, there is a cancerous tumor which a surgeon cut it from the kidney, and the leftover part is the healthy kidney tissue. Right. So they have selected that 13 different patients having a high score of this on a nephrometry, and basically they have printed the kidneys with tumor. You can see over here this white, blue, yellow, and this magenta. These are the tumors, right, in that kidney. And then doctors and the surgeons sit together, and they have basically observed the shape of that particular tumor, the size of that particular tumor, and the location of that particular tumor, right? And they have planned, or they the approach of doing that surgery, right? And after printing these 13 models, they found that the three surgeries were too complex, and they have to choose a different approach, right? And even on actual operation theater, they have followed that same approach which they have think in their mind before surgery, right? And the result was 100% satisfactory. This was you can see over here, this is a real tumor, and this is the dissected tumor on that 3D printed model. So basically seeing these kind of tumors in 2D, or you can say that 2D sheet of that particular MRI CT scan or an X-ray, you can see they cannot absorb that particular geometry or the anatomy of that particular disease, right? So it is very complex. So they have implemented 3D printing technology for this particular surgery. Right. The second example is again from AIMS, New Delhi. This time they have made this endoscopic surgery simulation device. This is a kind of, you can say, a medical training device, right? So in a neuroendoscopy, basically a neurosurgeon has to remove the tumor through a small holes, by in maybe in skull, in mouth, or through a nose, right? So in this surgery basically that the neurosurgeon has to be dedicated, trained to do this surgery, right? So for doing that, the surgeons have to be pre-planned, or they have to be pre-trained for doing this surgery, right? Because there is a the most important thing in this surgery is a eye hand coordination, right? So they have printed this dummy model of for neuroendoscopy surgeon. So what they have did, they have used FDM 3D printing over here. They have used ABS material, and they have printed this box. Inside that, they have created a mechanism like this way. They have created a hole at an angle similar to a nose or a skull, like they have to do in an OT. And they have inserted their medical device through that particular hole, and inside that they have fitted that sensor, right? They have created this kind of design inside that particular simulation device. And with that, the concept was they have to take that ring from one point and put it into other. Basically, you can see that A picture gives you a clarity of the horizontal movement, B picture gives you a clarity for the cross sectional movement, right? That they have fitted that sensor within this device, and that sensor will detect whether the movement of that hand was too fast, or it was too slow, or like it was distorted, or it was not clear as it should be while in the surgery, right? So accordingly they will get a grade, that surgeon will get a grade. Okay, he's ready to do that surgery in an OT, or still he's in a training phase. So like that, they have developed basically an endoscopy simulation in their lab. This is from example from AIMS. This was is from Oxygen Medical. Oxygen Medical is basically India's number one orthopedic implant manufacturers and exporters in Sonipat, Haryana. They have FDM 3D printer, and they are using this printer for printing again human anatomies. Basically, they're a manufacturer of the implants. So what they done is they have printed this anatomy. This is a fractured bone anatomy, and they have printed this, and then they have fitted the implant over it to check the fitment of that particular this wise lock plate. They are a manufacturer of this plate. So to check the fitment whether the plate was good or not, so they have printed this uh, bone, fractured bone, and then they have basically checked the fitment of that particular metal implant. In the second case, they have printed this spine model. The spine was in blue, and invertebral disc is in white. After that, after checking the fitment of everything, they have printed this in, like they have manufactured it in metal titanium. Then this was again an example of a patient-specific maxillofacial implant. They have 3D printed the anatomy of that particular patient, and then they have reconstructed the implant for that particular anatomy. Then they have printed that implant to check the fitment. Once everything is done, then they have manufactured it in titanium. So basically, instead of directly using a tooling or a CNC or a machining, they are using 3D printing for first clarification for the prototyping phase, and then they are directly using the tooling at the end, right? This is an example for medical devices casing. They have 3D printed this power tool casing with FTM technology on an ABS material, right? So now, the fourth example is from Ludhiana Mediways Hospital. Basically, they have used polyjet 3D printing technology. The idea is basically that surgeon get a case in which there is a large connection between which was bypassing basically the lung, and the blood was entering into the lung without taking that oxygen. Right, you can see that case over here. The nails get completely bluish because there was no oxygen which was bypassing into the lung, right? So they have 3D printed from that CT the data, they DICOM data, they have basically segmented it into an STL model, and then they have 3D printed that particular anatomy, and they have seen the correlation between the anatomy, and they have get the idea of how to plan a surgery for that particular patient, right? Because they have already like pre-planned the surgery. So while OT, this was the result. You can see the blood loss reduction was 90% because they already know the concept. They already know, okay, this is anatomy. This is way they are going to basically cut it out from that patient, right? And the surgery time was also reduced to 35%, right? So basically, this was the whole concept. This is a major application of 3D printing in the healthcare industry, where surgeons are basically pre-planned the surgery so that the risk of the patient life is drastically reduced, and the surgeon and the family members are also sure that the patient is going to survive. Right. This is one example. This one is an example from Manipal Hospital in Bangalore. So basically, they are also get a complex case for a neurosurgery in which there was a tumor in that brain, and they have to basically cut out that tumor from that anatomy. So again, it was a very big tumor, and there was a challenge to basically rectify the position of that particular tumor as well as the shape of that particular disease. So what they have done, they have again dissected this model in a medical software, and then they have 3D printed it in a four sectioned way, so that they can basically it is good to handle that particular model, right? And then they have used a combination of soft as well as hard material. They have given the tumor to a different material and a different color, and then they have printed the brain with a soft tissue, and they have dissected, and they get that idea, okay, this much is a big tumor at this location, and they have pre-planned again that surgery for that particular patient, and the patient life gets saved. So the printing time for this whole brain with tumor was 8 hours. You can see multiple materials have been used with rubber as well as rigid material. So this is how a 3D printing works in medical healthcare solution, right? This one more example from UIT Chandigarh. They are basically this is basically a college, but they have set up a design innovation center at UIT, where they are developing medical devices for various hospitals. So this was an example for a bite force measuring device. The inputs was given by Dr. Anand Gupta here in Government Medical College and Hospital Chandigarh. So basically, and the idea of this device was to assess the biting force related disorders and the recovery rates of the post-operated patients. Like the patients which are get now treated, then they have to check how is the treatment going on, or whether the bite force is now good or it is still low. So accordingly, they will plan the further surgery for that particular patient. So they have 3D printed this model, right? Even everything electronic sensors are fitted within this model, and then they have put that model into the mouth of that particular patient and ask them to bite a strong bite, right? And accordingly the sensor will give a value with which a surgeon can detect whether the biting force was normal, good or bad, right? So accordingly they will plan a further surgery. This one is example from neuro hand guide. Basically the 3D printed gloves which was equipped with an elastic tensioners, right, to give that assistance for that particular patient. This one again 3D printed model, right. The last example is from the IIT Bombay. Basically, they have set up a BATIC lab, biomedical engineering and technology incubation center. Right, they have a Fortis solution in house, and they are using ABS as well as high performance materials and biocompatible materials for the medical devices. Right, till date, they have basically come across a 400 different medical problems collected from more than 100 doctors from different hospitals, and they have challenged each and every problem with the help of 3D printing, right. So you can see the first part is the 3D printed leg processes, in which they have printed a socket in the ABS thermoplastic material, right? And then they have designed that processes and fitted into a patient. Second example is the 3D printed prototype of a laparoscopy instrument. Basically, this gives the design was so good that it reduces the stresses for that surgeon while operating, right? The first one is a concept prototype that they have made with the help of papers, and then they have 3D printed this one, and at the last they have made a metal prototype, right. So the third example is this digital stethoscope, in which they have printed a casing of that stethoscope where sensors and electronics are fitted with the help of 3D printing solution. So this is a concept of how 3D printing is helpful in aerospace, defense, and healthcare application. So basically, I'm open to take a questions. If anybody has any question, you can ask. Thank you so
Thank
much
you.
for
Thank,
this.
yeah, thank you, Shubham. Thank you for
Yes.
a wonderful session. We were even thinking all these are happening in India or what? Because whatever we are
Okay.
checking on with that, like you're pointing out each and every example, someone over here and there in India, and we are just wondering like all this
Yes.
research are happening in India. Cool. Like participants, if you have
Yeah.
any queries, you can directly put to Mr. Shubham. Like he'll be happy to answer your queries. Because whatever we saw, everything is from India. It's not like we
Yeah,
get
everything
from
is from
some other
India. Yes.
countries. Anyone, any queries?
Anyone want to know some other applications, or let's say how still if somebody has doubt that how they are basically using the concept of 3D printing, you can ask.
Sir, good morning, sir.
Good morning.
Okay. Am I audible?
Yes, yes. Continue,
Yes,
sir. Good
yes.
morning.
Sir, I have some doubt regarding you have mentioned about some soft tissue issue in dental. Uh,
Correct.
yeah. And what is actually I heard bone grafting and something related to this in dental related field.
Okay.
Because can you have any idea about what is the recent research going on the dental bioprinting area other than
Okay. So in basically in dental industry, there are 4 5 areas where 3D printing is applicable. Okay, the first one is the crown and bridges application, where you can directly print a model of that crown of that base, and you can basically check the fitment of that particular crown on that model. Right. The first application is the crown and bridges. Second application is the aligner, where you can basically again 3D print a base of that particular model, and you can then thermoform the sheet of that aligner, and or with that help of a base model, and then you can basically fit it into a patient mouth, right. The third application, where a few materials are available which are long term biocompatible, and with which you can directly print that dental guides as well as this tooth, and you can basically fit into that particular patient, right? So these 3-4 areas are there within the dental industry. Apart from that, the maxillofacial surgery, where basically you can print an anatomy and then design an implant, and accordingly you can check the fitment of that particular implant with the help of an anatomy. So these 3-4 applications are available within the dental industry by 3D printing.
Okay, thank you. Thank you so much, sir. Thank you.
Any other queries?
Hello.
Is there any other queries from anyone?
Hello. Good morning, sir.
Yeah, good morning, sir.
Prasid.
So my question is that can we design the mask of our face exactly same with the help of 3D printing?
Mask of that face, the mask should be a flexible, how it is.
Yes, sir. Flexible. It should be flexible so that we can,
Yes.
anybody can wear it on his
Okay,
face.
okay. So far, actually, in outer countries, there is one company. They have basically 3D print mask in polyjet flexible material. But since the materials are not biocompatible, so they have put a coating. I'm not sure about that particular coating. They have done a coating on that particular mask, and with that, they are using and they are wearing that particular printed mask with the help of polyjet 3D printing. They have printed, right? Because so far the materials available within the 3D printing polyjet technology, they are biocompatible up to a 24 hour. After that, you have to do a sterilization to further use, right? So but in outer countries, they have developed this kind of concept. Apart from that, I have seen where they have basically 3D printed a patient face as a mold, and then they have used a thermoform sheet and get that particular mask, like that they are using so far I have seen.
Okay, sir. Thank you.
Thank you. Is there any other queries? Further? Participant, any other queries? Sure, it's good to see too many people asking queries. Like, sure, we have made the session too good for us. Like, there is one more question from
So,
Dr.
sir,
Gunashekaran. Yeah, proceed.
will that mask will be exact to our face now?
Yes, sir. Yes, sir. Basically, the idea is you 3D scan your face, you get the anatomy of that particular face, and then with the help of software, let's say 2 thick, you will design your particular mask. So that the idea is something like that.
Okay, sir.
One more query from Dr. Gunashekaran, whether we can use metal filament in FDM.
Okay, so yes, there are printers available with which you can print metal with the FDM 3D printing solution. So the material name is 316L stainless steel. It came from BASF company, right? But that particular printed model you cannot directly use for a end use application, because it's kind of a green part. You have to do a sintering process, and after sintering, that part will achieve a metal properties, and then you can basically directly use an end use. So the possibilities are there within FDM printing solutions.
I think sir answered the question. Okay. One more question. What would be the best method for reinforcing polymer filaments? What would be the best method for reinforcing polymer filaments?
Reinforcing polymer
Polymer
filaments. uh, uh, what I have observed, like the composite tooling, with the example which I have given, companies are using, because so far in FDM I have seen an nylon carbon fiber material, and ultim material, and ABS carbon fiber material, polycarbonate material. Those materials are available within the photo solution, which are high performance materials, right? But if somebody need a specific carbon fiber only, like not nylon carbon fiber or something, so what they are doing, they are basically printing their models with water soluble support material, right? So there is a material called ST130 within Fortis solution, right? So you can print your model with that particular material, and you can wrap your composite material on that particular geometry, and then dip it into a water, or that R material, which is ST130, will get dissolved, and you're left out with their composite part. So that kind of application is possible within 3D printing solution.
And even now, few startups have been also started in Delhi based. Like there are some students from VIT, they are doing the same thing. I guess, like if I'm not wrong.
Yes.
Thank you. Right. Thank you, sir. It was a wonderful session. I could see too many people got involved in today's session, like more than other technical talks. It was more on interaction. They have clarified all their doubts. Thank you for the wonderful session for us. Next, we'll move on to Ms. Aishwarya Shirur, technical specialist, to explain few aspects of 3D bioprinting. Over to you, ma'am.
All right, sir. Just a second. I'll be sharing my
Yeah.
screen now.
Yeah.
Yes.
Yes, ma'am.
So hello, everyone. A very good morning. And I think Shubham has already explained quite a lot of aspects of bioprinting, basic printing to everyone, which is 3D printing as a technology in healthcare. And now I'll be coming down to how you could innovate and how you could use 3D bioprinting as a technique when it comes to applications in healthcare and life sciences. And again, I'm Aishwarya Shirur. I work with Altum Technologies. Uh, Shubham has given you introduction of the company, so now I'll just begin with the main topic. So when we talk about life sciences, we have a very basic idea when it comes to using pharmaceuticals or any drug discovery or developmental process. We would have maybe compound exploration, characterizing the drug, clinical implementations, and these steps take quite a lot of time. And when you come down to these, all of these studies that occur are actually something that happen in the 2D space. So while they happen in the 2D space, there is also a large amount of steps that it has to go through in order to get to it. And while you're going through these processes, you will see that the time consumption is high and quite possible that there's also a possibility of false negatives and false positives when you're giving the outcomes. So we have solutions on our end, which is one is in silico analysis, being virtually being able to find the models and the drug development aspects, and next being the drug characterization, where you could use 3D biofabrication. So that's where we have Cellink. In order to us for us to understand what is 3D bioprinting, how it is impacting in terms of cost and in terms of time, and how being 3D in structure, these will help in the development of tissue engineering as well as any other biological aspect. So the challenges that actually exist right now, as all of us know, is that there's a lack of organ transplants, there is waste due to wrong testing methods, and then you have this lab to shelf time. So all of these are existing issues and they will remain for quite a lot of time, but the idea of 3D bioprinting is actually to bridge this gap, to shorten lifespan of getting maybe an organ transplant, that is while trying to create artificial organs, or trying to shortline or improve the time of testing methods. So I'll be talking about again 3D bioprinting here. So it is a form of additive manufacturing, as we all know. Except here you're going to use cells and other biocompatible materials. These biocompatible materials are called bioinks, or also known as hydrogels. So they are printed in a layer by layer fashion in order to mimic the natural living systems. So when you talk about 3D bioprinting as such, it is taking the key concept of 3D printing. That is, we have seen metal or plastic printing, except along with it, you have to use the idea of tissue engineering. So tissue engineering is actually a technique or technology wherein you have multiple, areas or facets of science involving in mimicking the form, function, fit when it comes to the human body. And the essential components when it comes to 3D bioprinting itself involves cells, bioinks, and culture media. So these are the basic components that you would say are required in 3D bioprinting itself. So as you can see here in this image, you see, this sort of color or a dye, which is just printing something like a nerve-like structure. So the idea here was to create something as close to maybe creating a kidney model, right? So right now we are progressing towards we are right now in the research phase, and we are progressing slowly with time towards making more functional models, making more viable models over time. And in bioprinting, there are quite a lot of types of bioprinters or the techniques or technologies which are used. But extrusion printing is one of them, which is quite used, where it is pressure assisted. You have filament dependence. It is where you can create multiple models, and you can also use multiple materials. On the other hand, we have something called digital light processing. So digital light processing is light assisted, filament independent, and it's known to create high resolution watertight channels and watertight models. Except on this side of bioprinting itself, there is a limitation in terms of the material usages. So if you see this, you will see that there is extrusion happening. There's pneumatic pressure, which is through a print cartridge, which allows the expulsion or the extrusion of your ink. So in this manner, the print heads are moved. So they definitely use the idea of 3D printing itself, except it's just the difference of material and what are your applications towards it. And this is the light technology, which is DLP. So when you have to create something as complex or even more complex than this, then you would definitely go for light processing as a technique. So the steps that are actually involved, we are quite aware of what steps happen in terms of normal 3D printing or plastic printing. Now I'll just take you through how it works when it comes to our bioprinting. So one thing is, either you will take the data. We are looking at printing biological models. So you would take the data from maybe anatomical data which is available in order to mimic it through papers, through forums where you have models available. Following that, you have your MRI scans. So right, so once you have the MRI scan, you can always convert this data when you want to do any sort of customization. And the other aspect of it is where you could even use 3D scanning in order to attain these biological data or any sort of physiological aspects. So the step here is called imaging, right? Once this is done, you come to a point where you have the 3D design aspect. So you convert your DICOM images or the 2D slices into a 3D format where it is called design. So this is where you do the design, and you also convert your STL file into a G code. And from there, we come to the main aspect of bioprinting, the essence of bioprinting, which is material selection. So in material selection, it is actually that you would use materials which are naturally available. That is the most preferred way in terms of biocompatibility. So while we are selecting a material which is biocompatible, we also might need to consider the mechanical aspects of it. So with that, we have cell selection. So another aspect of this, where you have cell selection happening, you will have to see what application you're working with. So if I want to create skin, I'll have to take fibroblasts or keratinocyte cells or whatever essential components are there that constitute skin is to be used. So on these bases, the cell selection and material selections are done, and they both are blended together. And this is called the bioink development, or this is called the material development aspect of it. Once that happens, you go through a phase wherein you select which method you want to use. So this is the processing part, selecting which type of printer you want to use. So you can use extrusion based printers, or you can use DLP based printers, depending on the kind of complexity of the model, depending on the material you want to use, and what is the kind of strength, what is the kind of degradation time, what is the cell viability impact that you want to see, which will help you out. So from here, we have the next step, which is the UV curing process. So it's also called the cross-linking process. Following this, we go through incubation time, that is the growth or differentiation time. So when it comes to cells, you have to allow them to mature, allow proper cell signaling, better interaction between cells, as well as there is a need for us to know whether our cells are growing properly. So from the maturation phase comes the point where we have maybe the in vitro testing or the application, or you could just call it as a final step of bioprinting itself. So this is a basic steps that you would take. It's quite similar to 3D printing itself, except there are some minor aspects of it which are quite important, quite crucial, say material selection, cell selection, and even finding the technique, and then incubation and in vitro testing. So applications of 3D bioprinting, we are at a forum right now where we are talking about uh, 3D printing as such, how 3D printing is used as a tool for a lot of applications, when it comes to maybe aerospace, when it comes to healthcare in general. Now we are coming to a segment where definitely it is a more biomedical or a biotech specific, life science specific, but there's always a need for considering the mechanical aspects when it comes to printing. So the applications are quite diverse when it comes to them. So say we start with soft robotics. I'll go on explaining each of these sectors one by one. So soft robotics, following that we have biomaterials development, there's organ on a chip, tissue models, drug discovery, 3D cell culture, complex model designs, as well as drug delivery. So when you come to soft robotics, the idea of soft robotics is going or mimicking the human body or any animal structure, except with compliant materials. So when we talk about robots, they're usually made of rigid forms, right? So they are metallic, they have a very specific set of motion, and they are not very compliant in that way, like in terms of elasticity, in terms of rigidity. These factors are quite important. So when you use soft robotics, you're actually trying to create something which is more natural in terms of mimicking, say example, the tentacles of an octopus or any other part. So that is where soft robotics is actually helped using bioprinters, because you'll be developing different types of materials. You can use these materials to create even the most minor structures, and with these minor structures you will obviously add maybe sensors or create smart materials, etc. With soft robotics, there also comes a section which is called biohybrid soft robotics. So this is a combination of material science, biomechanics, sensing, and cells. So having cells involved in it is also quite fascinating, because you could use this in a lot of ways, say example in terms of surgeries, in terms of diagnosis, in terms of understanding and mimicking the behavior of organisms. So I'll give you 2 3 examples here, saying the development of a basic material, a combinatory smart material which can easily flex in different angles, considering the design of it, considering the material which is used, and seeing the swelling factor of it, to see how you can use this as a good standard material when it comes to developing any other form, maybe a tentacle, maybe any sort of gripping hold, there's a normal radial expansion tube, etc. So another example here is using magnetic materials. So using ferromagnetic materials or biocompatible materials which are more ferromagnetic can actually help in most of the surgical modeling, because one thing is you will be developing your own open source materials where it is applying better in medical devices. So having these and creating basic design models, testing the materials, and then finally coming to a conclusion as to where I want to use it the best is quite an important aspect. Following this, it is the biomaterial development, which is very interesting, and there's a growing need for a lot of mechanical engineering tools and design aspects to it. Say example, there is a material which is hydroxyapatite, right? So when it is available to a doctor, it is available in the form of beads, or it is in the form of any standard dimension. Now I want to use this on a patient, so I need a set of customization that needs to happen for that patient to be using it, right? So the example is going to be a radius ulna fracture, and we are trying to create a graft material. So in order to do that, you need to modulate your material. You need to change the texture of the material and also create something which eventually is more stiff, more mechanically compliant. So using bioprinting or using just normal bioprinters as a tool would allow you to create biomaterials along with maybe thermoplastics, mix them together, blend them together to create a basic design. So this is a case wherein they have done the patient defect detection, they have taken the CT scan, they have done the segmentation and reconstruction. Following that, they have done the CAD design. When they've done the CAD design, obviously they have come through a process where they've done a normal printing of your graft. They've tried to understand what is a pre-surgical modeling requirements when it comes to normal 3D printing. And using those pre-surgical basically time and position aspects, you would translate that when it comes to using it on a patient, right? So when it came to using it on the patient itself, they were able to reduce the time span, they were able to easily design the graft material they wanted, and they incorporated in the bone site, allowing a good amount of regeneration or growth at the site of the patient. So aspects when it comes to bioprinting here will definitely rely on infill, which is a very common term all of us know about. Except since we're using biomaterials, we need to understand which is the right infill that we can use, what is the kind of extrusion, what is the kind of pressure required to extrude this material. So there's a lot of optimizations and customizations that need to be done when it comes to developing materials that are more biocompatible. Next comes 3D cell culture. Again, this is just say a rough example for you to understand that a 3D environment is quite crucial for the development of complex structures and also for the network formation of various cell types. So when you look at or when you compare how your 2D versus 3D formats of cells are, you will see that the 3D ones have a better phenotype, a better physical arrangement, a better sort of arrangement of the cells. So that's where it's quite crucial for the development of complex structures, and it allows you to understand the different models quite differently. So endothelial cells or stem cells or liver cells. Now we come to the tissue engineering idea. Like the whole idea of bioprinting actually started from here. They were using conventional methods to create scaffolds, use these scaffolds, seed them with cells, and then after they seeded them with cells, they would try to see what is the growth of the cells. Is the cell viable? Is it living? Is it able to produce the functions that it is asking for? Right. So here it's a case where they try to just understand and see what is the effect of using a 3D bioprinter in terms of the cell growth, in terms of the viability, and also the biochemical factors um, in terms of what heart cell. Example, you're using a heart cell, right? So they went by the processes, saying using the CAD model, using a material, and this material is actually a predefined or a pre-optimized material, which is called as a cell link lamining. Mixed it with the iPSC cells in a specific concentration, printed it using a bioprinter. Again, the designs here can be very simple and also can be very complex. So here they have just taken a very simple design, try to see what is the impact of using cells when it comes to bioprinting. So upon bioprinting, they went through the UV curing process, etc., and they went to incubation. And in the incubation, now this is
Hello, Aishwarya? Hello? Hello? Aishwarya, I think there's a drop in the call. Hello.
Yeah, let me just connect with her. I think there is some network problem.
Okay, okay.
Oh, she's connected. Just a few
Okay.
seconds.
Okay.
Use your hotspot. Yeah, continue.
Yes. Sorry for the delay there. It's a small
Now it's
minor
okay.
glitch.
Yeah.
Yes.
Yeah.
Yes. So yeah. So I will just step back to this where the bioprinting has happened and the incubation process takes place. And with the incubation process, it takes about 3 weeks or so, where the tissue basically matures. So upon maturation, you would see that when they did the culture studies, they were able to see this sort of beating sort of a motion. So that is actually the inflow and outflow of calcium, which denotes that this is how cardiomyocytes are in nature, and this is how you would see when it comes to bioprinting used as a technique. Um, so from here we go to complex designs. Uh, this is an application which is very interesting and quite fascinating when it comes to the healthcare sections, in terms of developmental studies, in terms of understanding what is the most important factors when it comes to the organogenesis, that is the organ development process, or what could be the factors that could cause any sort of diseases. So here it is again a heart model which they try to print. Here they have taken patient specific models. So they would do a comparison between the embryonic heart and a fetal heart in order to understand what is the developmental gap and what are the factors that influence the development of heart. So the idea here is to see if you would understand upon your scanning methods, your maybe CT or MRI scanning, where you will see what is the first developments. Example, in embryonic heart, it would be the tube structure, which is first, the heart tube. And then when it comes to the fetal heart, it is the ventricles which are formed. So they try to take these images, retrieve the images, and create subsequent models. And while creating the models, they use DLP as a technique, and they use material called gelma. And upon doing that, or after doing that, they seeded it with cells which are endothelial cells. So when they did the seeding of the cells, and along with that, they also did some perfusion studies. So when they did the perfusion studies, they were able to do the perfusion quite consistently, also to see that how is the impact of this perfusion or the microfluidic aspects that might influence the growth of the cells. And upon analysis, they were also able to see that, okay, fine, if the pressure that is flowing, the pressure of the blood flowing through the heart, or if the cells have not developed properly, then what could be the impact in terms of congenital heart diseases. So the analysis kind of brings in and helps in understanding the outcomes of most cell development aspects. Next is organ chip, which is fascinating in a lot of ways, because it uses the idea of microfluidics here, and with that, you would go on with using maybe chips in order to understand the drug discovery or the drug development, and to know if you would want to make something like a lab on a chip. And using this, you would take it as a basic culture format, sort of diseases, any quick testing methods, etc. From there, we have drug development. So with drug development, you have throughput screening of your drugs. Basically, you're creating a model, and on the model, you're trying to understand the toxicology, basically the toxicity impacts of any sort of drug on a particular cell type. So in this, you can use either one type or several types. So it kind of reduces the timeline when it comes to studies, because now you're also testing it on a tissue directly. And you will understand what is the collagen deposition, maybe there is a ECM production, what is the effect of the surrounding tissues, and you can also understand and give a predictive model saying if I use this concentration, there is this impact on this drug. If I use a different concentration of that same drug, again of the different family or the same family, what could be the impact? So predictive correlations can be done, and also you'd use it as a very nice model. And right now, since bioprinting is still as at its research phase and a lot of people are understanding how it can be used quite effectively in the area of healthcare and life sciences, there is a good interface that you can see in terms of diagnostic development and how 3D bioprinting is used. So example, simple models are used. Then you can use disease models where you can use maybe complex or multicellular models. Then you can go to toxicity screening where you want to see the toxic impact of any drug on two or different organs of the body. And then there comes precision medicine where you would use patient specific cells for diagnosis. And you can understand what sort of treatment is best possible for the patient. Next is drug delivery, which is fairly simpler comparative to the rest of the parts, where they try to create basic models, basic designs with hydrogel materials, with the medication that you require. So this is example of a biopierce. So any normal piercing that you have will have an infection. So to avoid infection, to allow sustainable release, to give an application of drug at that site of piercing is a very simple example I can give you. And here they do the development of that. They do the testing in terms of NMR studies if there are any byproducts being created. There is also mechanical testing where you do to see what is the strength of what you have created, the hydrogel you have created, and how it will fit perfectly at the site of your piercing. They also do the sustainable drug release, the zone of inhibition studies, where they will see what is the impact of this drug over this time, over this area, and what can be improved over time. So using these simple tools, using bioprinting as a tool can actually help you in creating the most simple things when it comes to the biological systems, example, films, patches, you know, solvable or dissolvable sort of capsules using hydrogels, because again they're biocompatible. So these are many areas where you can use it. So the selling solution, as in what are the kind of bioprinters that we have, are quite diverse, varying from the technique, varying from the number of print heads, the complexity of the machine, and the simplicity of machine. So with this, I end this session. Thank you, everyone. If you have any questions, I can take them for you.
Thank you, Ishira ma'am. It was a wonderful session. Like, can you
Thank you,
just
sir.
put some insight to us, like what is the research aspect that is going on in India in this particular domain?
Okay, sure, sir. So
Yeah.
right now in universities or in research institutes like IISc or Guwahati, etc., they are now trying to take care of the biomaterial development aspects.
Okay.
So that's where they're doing quite a lot of extensive work. They're also trying to create artificial cartilages. Some people are in the segments, like there are startups in Bangalore itself where they want to get into creating organ on a chip models, more vascular models. There are several examples to quote, honestly. But the recent work or the most effective work that is being done right now is in terms of biomaterial development, considering
Okay.
the various facets of hydrogels we have available with us.
Cool. That is great to know, because like when I was discussing with people, they told like it will take at least 5-10 years to get things happen in India. But it's quite fascinating
Yes,
to know
yes.
things are happening right now.
Things are
Participants,
actually happening.
yeah.
Yes.
Participants, you have any more queries? You can rise up, like, because this session is literally making us think beyond what is happening in India.
Yes. Yes. Anyone with more questions? Hello.
Yeah, proceed, sir. Yeah, Nilesh, sir. Yeah.
Ma'am, what is the cost of these bioprinting machines?
One second, sir.
Yeah, sir, it depends on the technology you select, sir. As Aishwarya was sharing, there are two technologies. One is deposition based, second is DLP based. So based on the selection of technology and applications you choose, you will have to select the machine, sir. We will discuss on this. We will definitely connect you, sir.
Neil, sir, I'll connect you with Sridhar, sir. Like he can give you a lot of input about what is actually happening with that. Any other queries? Because what all I could feel is Aishwarya, this is completely out of box thinking. We never thought like these things are happening in India. Actually, like people are not even thinking about it or how it will happen. But it's like quite more interesting to know something which is happening within India, and we feel we are developing in a faster rate. That too in additive based 3D printing of bio implants as well, like bioprinting as well. It was a wonderful session organized from Altem Technologies. We are grateful from NIT Srinagar in this particular case. Thank you for Shubham, Aishwarya, and of course Sridhar sir for organizing this session. Thank you.
Thank you. Yeah.
Thank you, sir. Thank you.
Thank you.
Thank you. Participant, our next session will start from 11:30.